I've been with Nvidia almost 10 years. I've started in academia, researchers much like yourself. After completing Stanford University, working on parallel computing and parallel programming models, I came to Nvidia and created Cuda, and have been working on it ever since. My talk today is to give you some perspective of the history of GPU computing, as well as where we are today, and some of the things we need to work on together in the future. This is early work in GPU computing came from academia. Many researchers, such as myself, recognize the opportunity for GPUs to do more than just graphics processing. What motivated the original research into GPU computing was around the time of 2002 to 2003, GPUs started to become programmable. They moved from a fixed function graphics pipeline to being able to run very limited instructions per every pixel. But it was the beginning of programmable graphics. What was observed in research was that the performance of these GPUs started out fairly meager, only 10 gigaflops of performance. But very quickly, every 6 months to 1 year, they would grow at an amazing, alarming rate in terms of their performance. And at the same time, if you track the fastest CPU available, they were only growing moderately. And many researchers saw this trend and said, well, can we use these GPUs for general purpose computing? Because they seem to be very good at converting transistors into performance. In fact, during this 18-month period, we saw a 1.8x increase in the number of transistors available in GPUs. There was actually a 20% decrease in clock rate. They actually went slower in terms of their clock speed. But their performance went from 8 gigaflops to 53 gigaflops, or almost over a 6x speed up. This is an amazing trend in programmable performance. If you think about it, why were they able to do this? Why were GPUs motivated to become faster and faster? Was largely the work of trying to create photorealistic rendering in real time. Think about this is a screen capture from a facial rendering at the time, running on a GPU, with an immensely complex graphics program running on every one of these pixels to compute the lighting conditions, the subsurface scattering in the skin, as well as any reflections. It was a very complicated program. That program was run on every pixel in this entire image for a 30th of a second, and then we did it all over again. So 30 times a second times a million pixels. This is a massively parallel problem that graphics was solving. So as Moore's law was giving the GPU more and more transistors to work with, GPUs were excellent at turning those transistors into performance because they're trying to solve these really complex problems. Similarly, in trying to render lush, rich outside environments. And then we also started to see physics and game physics being accelerated by the GPU. Early GPGPU in 2002 looked at doing can one map a specific algorithm to a GPU. This was the first ray traced image with a GPU in 2002. Other people worked on PDE solvers, matrix multiplies. A bunch of papers published that said GPUs can do matrix multiply, they can do ray tracing. But after some interesting work demonstrating the possibility for GPU computing, the larger question became, how does one program these things? Because clearly, graphics APIs, DirectX and OpenACC are not the right answer for how you want to program GPUs. So they demonstrated that we had performance, but you really needed a PhD in computer graphics to do GPU computing at the time. And in some cases, some financial companies were hiring game programmers to try to get access to the GPU's performance, which clearly is not the right answer. My research and many of my colleagues at the time shifted from understanding what algorithms can run on a GPU, to how should we think about the GPU as a processor. This led to the work I did at Stanford University called Brook. Brook was a very simple extension of C to provide around the concept of streams, which were a fairly constrained, simple way of managing data on a GPU and executing kernels or small programs on a GPU under the constraints of early graphics hardware, programmable graphics hardware. This research demonstrated that it is possible to execute a general purpose language on a GPU, and inspired much of the early work that eventually became Cuda today. The challenges, however, of graphics, of general purpose computing at the time, was the constraints of what graphics hardware was. It still Brook had to be compiled down to a graphics API, and graphics at the time had constraints that were quite difficult for general purpose computing, such as very limited texture size or memory. Access to memory was constrained. There were very limited outputs. In fact, you could only write to one location in memory. A program couldn't write to any place in memory. It could only write to the one pixel that the graphics pipeline decided it wanted to write to. The instruction sets were fairly limited. There were no integer operations. You couldn't add two integers. You couldn't do any binary operations like an AND or an OR. Every instruction was either control flow or floating point arithmetic. Quite difficult to claim you're a general purpose processor if you can only do float. More importantly, communication was fairly limited. There was no way for one program to communicate with another program or function that was running right alongside it. And this led to very inefficient forms of computation. Many of these programs were doing the exact same calculation, but not sharing any of their data or results. So upon finishing the research at Stanford demonstrating that GPUs can be programmed in a general purpose way, albeit limited, I came to Nvidia and we looked at the graphics architecture at the time and said, what can we do to the graphics pipeline to make it general purpose? This is what the graphics pipeline looked at the time. This is a GeForce 7800 pixel pipeline. It took a set of input registers. These are input parameters to the function. Had a fragment program and then an output registers. And then memory was accessed through texture or constants. The first thing we did is introduce the idea of a thread program. This is the function that's going to run on the GPU. And each thread program was given a thread number, and that was the identifier to indicate what to the program, what should that thread execute. The thread program was generalized to support millions of instructions, no practical limitations. We added the integer instructions, the bit operations, all of the data types you need to implement a general purpose programming language like C. Relaxed the limits on branching and looping, and then provided a thread ID. In fact, we actually, not just a 1D ID, but a 2-dimensional and 3-dimensional thread ID in case you're doing image processing or volume processing. The next thing we did was generalize access to memory. Before Cuda, the only way to get access to memory, to write to memory, was the one pixel that the shader program was writing to, because that's all it needed. Instead, we were provided general global memory access, so a general load store to the GPU memory, also called scatter-gather. The programmer had complete flexibility in how memory was accessed. They could access any location on the GPU's memory, and it was untyped. Raw pointer support was there. The third thing we added that was very important was shared memory. This is something that the graphics pipeline didn't have before. Was a way as a dedicated on-chip memory that allowed a thread program to communicate with other thread programs running at the same time, so they could share results and share data. It also provided a good place for temporary data, for or blocking of algorithms, and important for improving performance. So where we came from in CPU, where you have a control logic, a cache, and the data sitting on the DRAM and the cache blocking it, Brook provided access to the graphics pipelines, but all the data had to flow all the way in and out of the GPU. With the introduction of the shared memory, we can now let these different processors share results and cache the data explicitly, manage the data explicitly on the GPU, further improving performance. This memory was as fast as registers to access, to read and write. Once we've built that architecture, we have to program it. So we built, and based on a lot of the ideas from Brook, Cuda. Cuda was a very simple, explicit programming language solution. The idea was not to invent a entirely new parallel programming language, but to keep it very simple. Extend C only where necessary. If you understood C, learning Cuda should be very easy for you. We added a couple of keywords, like this global keyword, to indicate that this function should be compiled and run on the GPU if called, and the shared keyword to allocate variables that live in that shared memory. And then we added this, the only syntactical change was this angle bracket syntax to indicate that this was a data, call this function many times with this many threads. In addition to those extensions, we added a runtime support. So if you know malloc and free from C, there's a Cuda malloc and Cuda free, which is just like for allocating data on the GPU. And then memory copy, memcopy to move data back and forth, just like C. And this was it. This is try to make it as easy as possible for C developers to parallelize their code and move it to GPUs. There's a couple other very subtle but very important additions that Cuda enabled. First, we recognize that the GPU is a massively parallel processor, but it's also when you have tens of thousands of threads running at the same time, you need to think of it as a data parallel processor. But data parallel programming at the time was very abstract. It dealt with data arrays and operators on arrays. What Cuda did is provide a threading view of data parallel programming to make it very easy to anyone who understood the basic concepts of threads to write a data parallel program. There's no need for accessors or views or operators. It also generalized it in the sense that the user could decide what one particular thread did and what memory it accessed instead of trying to constrain the problem around a set of data parallel primitives. The other important thing was it removed the divergence pain from parallel programming. Up until now, parallel programming was all about SSE, or vector operations. And developers had to program SSE or vectors explicitly in their code, which worked fine until a simulation or a calculation diverged because of control flow. A simulation hit the boundary of an object, and the thread now, the vector now had to split in half. The programmer had to write that code that managed the splitting. One important piece of technology that we added to GPUs was that divergence was handled in hardware, not in software. The programmer only had to write a program for one thread, and then it would do the SIMD SSE ganging of the threads together. And if they diverged because of control flow, it would handle the divergence for you. Made it much easier to gain the benefits of SIMD programming. This was the beginning of GPU computing, but we recognized very early that providing us access to the GPU in a general purpose way was only the beginning. We had to provide a solution for the entire ecosystem, not just how you program it, but deliver on all the features that people have come to rely upon with CPUs, libraries, tools, compilers, monitoring, networking. We had to not just program the GPU, but provide all that ecosystem support. And that was a challenge that we've been working on ever since then. and I'll talk about some of that ecosystem in a minute. Today we've reached, as Jensen mentioned in the keynote, over 350 million CUDA-capable GPUs have been shipped today. A very important part of what's made CUDA successful is that CUDA is everywhere. In the 5 years we've been shipping CUDA, we made sure that every GPU that's shipped by Nvidia supports CUDA to make sure that anyone can get access to it by simply downloading the toolkit and trying it out. As a result, we've had over 1 million downloads of our toolkit. We think we have over 120,000 active CUDA developers today, and over 450 universities are teaching CUDA, including here in China. CUDA will now be part of the standard curriculum for in Chinese universities. To grow the ecosystem is important. We have to think about the different kinds of users, because there's not just one user of developer in the world, or one type of developer. There's many different kinds. So we focused on providing a wide breadth of solutions for users. Not just CUDA-C, which I've talked about already, but many people could benefit from libraries or custom languages for their problem, or potentially even just ported applications. In addition to CUDA-C, we want to make sure we provide access to the lower levels of GPU computing, such that other partners can develop their own tools and their own languages to help build and grow the ecosystem. So in the very beginning of CUDA, we recognized the need for libraries. And so in when we launched CUDA 1.0, we actually made sure we had a FFT and a BLAS library at the very beginning. FFT, the fast Fourier, many people have algorithms which boil down to a linear algebra, matrix multiply, or sparse matrix, or single processing. If your program maps to those primitives, you can use one of these libraries, and it's a very easy way to get your code onto the GPU. Since then, we've grown the libraries to include sparse matrix, random number generation, image and video processing, C++ templates, and of course, the full C Math 99 floating point library. I believe we have probably the world's fastest FFT library available on workstations today. It is fully optimized by NVIDIA engineers to make sure we're getting the peak absolute performance out of our GPUs, because so many algorithms in image processing and signal processing boil down to a simple FFT. In CUDA 4.1, which is the release candidate is available today, we've made the whole API thread safe and callable from multiple threads, and we've added some new data types and transform types. Sparse matrix, many numerical solvers for fluid simulation, crash simulation, and mechanical engineering can be expressed as a sparse matrix solve. We've also added the addition of a sparse matrix library to solve equations like the one shown here, and provided a variety of different sparse matrix compression formats for this group. The other interesting library we did was random number generation. Turns out in the financial community, they have very complicated integral equations with hundreds of variables. So complicated that it would be impossible to solve the integral in a closed form. So the way you solve it is not by trying to do the math, but actually just sample it with random values for the variables. This is called Monte Carlo integration, to compute the integral of a curve by randomly sampling it. It turns out the quality of your random number generation, the speed at which you can generate high quality random numbers, is critical in getting an accurate answer. And in finance, it's very important to get an accurate answer. Otherwise, a lot of money is lost. So we've been working on, we provided now a random number generator. It's an example of the kinds of libraries you can provide, and they don't need to just come from NVIDIA to help build the GPU computing ecosystem. In fact, today, if I look at, these are all the different tools, libraries, compilers that NVIDIA and others have built in order to support end users and end developers. In fact, Nvidia only supplies a small number of the actual tools that are available on GPU computing. Many of them are, other companies are here at GTC Asia. Things like the PyCuda for running Cuda inside of Python. The Alinea DDT debugger for doing cluster debugging for multi-node, multi-machine debugging with Cuda. Or Magma. This is a huge linear algebra library for LAPACK. The other thing that we've been focusing on and to help grow the ecosystem is directives. We feel like providing Cuda and Cuda-C was the right foundational layer for getting GPU computing started. But as we're growing and trying to influence and affect more developers, we start to include people like physicists and mathematicians and mechanical engineers who are less comfortable with the concepts of parallel programming or programming explicitly in C. They would prefer to use a higher level solution or a simpler solution that gets their code onto the GPU and gives them performance. Directives are simple hints for a compiler to allow a compiler to automatically parallelize your code by indicating which sections of the code are compute intensive and that should be parallelized. You provide additional hints on memory usage, and by giving just a few hints, the compiler can do the heavy lifting of parallelizing the code and mapping it to the GPU. Makes it much easier, much more approachable for people like non-computer scientists to get access to GPU computing. In fact, to help this spur and get new users, we've announced a new standard for directive-based computing called OpenACC. The main providers of directives, PGI, CAPS, and Cray, and Nvidia have gotten together to create one standard called OpenACC. We have, I think some of these are out there. This is a quick start guide to that explains the directives and what they're available. In fact, it's a separate website independent of these companies. So there's one solution and one set of directives that developers can tackle. And I expect compilers for OpenACC to be available shortly, soon next year. In fact, to help promote directives, we've started a program called 2x in 4 weeks guaranteed. If you go to this website, you can download a free trial license of PGI's Accelerator product, which is what OpenACC is based on, and actually guarantee 2x performance in 4 weeks, or we'll provide free consulting to help achieve it. In many cases, we find that it doesn't even take a day. In real-time object detection, this user got 5x in 1 week. For evaluating stock portfolios using Monte Carlo, the same Monte Carlo techniques I talked about before, they are actually able to achieve 2x in 4 hours. And interaction of solvents and biomolecules, they got 5x in 1 day. Clearly, maybe they had some slow CPU code, but that's the point. These scientists are trying to map their algorithms into Fortran or into C as quickly as possible and get a result. If we can give them a solution that works in those timescales, then they can be much more productive, and they can solve problems much larger than they could before and get answers in a day instead of 2 weeks. The other thing that we're trying to do to help grow the ecosystem is to open up the Cuda platform. So many people have come to us and said, I'm interested in supporting new languages, either that exist today or ones in research that I'm developing for myself, domain-specific languages. And they want to map them onto GPUs. So to support those users, we're opening up the Cuda compiler. This is the compiler that we use to compile Cuda-C and C++ to NVIDIA GPUs. And that compiler infrastructure and source code will be available to those researchers or tools vendors that want to start and map their code, map their language to NVIDIA GPUs. In some cases, we also see that people want to map CUDA-C to new GPUs or new processors in academic research. Also very helpful for them. And you can apply for early access to the source code at the website below, or search our website. The compiler is based on LLVM, which is a very well-known open source compiler effort, which has taken the compiler world by storm. Apple is now using LLVM, Adobe uses LLVM. The other thing that's going to help GPU and grow are tools. Many users find it very easy to, if they're familiar with C, to add Cuda to their code or use directives and get their code on the GPU, but then they want to get more performance. And we've made it very easy, but they need to understand how they can get further performance. This is where tools, I feel, are critically important, especially profilers. Profilers like, we just released in Cuda 4.1 a new visual profiler. This will actually run your program multiple times on a GPU, read the hardware counters and the performance state, and generate a step-by-step guided workflow for all the places you can improve your performance in your application. And by clicking on any one of them, it brings you to the direct spot in the documentation that talks about that performance improvement option. In addition to where we are today, let's talk more about where we are going. I am very excited about the new work being done on new processors. For many years, x86 was the only CPU, and the x86 architecture and PC was the only architecture available for computing. But only in the last 5 years, we've seen new CPUs emerge, and some of the old rules and constraints of x86 are now being questioned, and new technologies can be developed. ARM is certainly very interesting for NVIDIA. We've announced an ARM development kit. This is a Tegra ARM CPU and an NVIDIA Cuda GPU, all in one computer. This is it runs Ubuntu, gigabit Ethernet, very easy to use, video connection, to help people move their code to ARM. In the computing space, people are excited about ARM because of its power efficiency. ARM originated as a power-efficient embedded processor. And as power becomes more and more critical in the design and building of supercomputers, people are looking to the ARM architecture as potentially being a better solution for supercomputers in the future because of its power efficiency. And to help accelerate that, we're going to provide a platform which will support all of our Cuda tools to help people bring their code to ARM. In addition, the Barcelona supercomputer is starting is building a cluster out of these GPUs, which we feel may hit the first ARM-based top 500 supercomputer by next year. Here in China, the Longsong processor, again, is another example of a new processor technology that's being developed. And if we look at there's a lot of opportunities to more tightly integrate and improve the technology that's available inside of these processors for interacting with the GPU, whether memory coherency, consistency, communication, synchronization. There are some things we can do in our CPUs to provide better access and better interaction with our GPUs today. Moving forward, what's motivating a lot of research and development at many companies is the challenge to build an exaflop scale supercomputer by the end of this decade, by 2020. An exaflop scale cluster may have hundreds of thousands of nodes, needs to operate in maybe only 20 megawatts of power. There are lots of technical challenges that need to be solved, but for NVIDIA and for myself, my goal is to provide those building blocks, whether it's communication with a GPU and a network card, new synchronization and atomic primitives, better integration of the GPU with the CPU and the rest of the operating system, or better and new opportunities for parallelism. We've been working on improving the communication between the GPU and the network adapter for quite some time. We call this technology GPU Direct. It allows a GPU to directly transfer data to a network card and back, either out of the GPU memory or from a direct load store from a GPU. And those transactions travel to the network card without involving the CPU or the CPU's memory, greatly improving the efficiency of communication. Potentially in the future, a GPU could write to a location in memory, and based on that location, route the store across the chipset into the network and back to the next GPU and store into another GPU's memory, all without the CPU ever getting involved. A second area that's very interesting is the how do we bring GPUs and CPUs closer together as one heterogeneous system? We've taken some early steps in that. First, we've unified the address space since Cuda 4.0. This means that there's one contiguous address space from the CPU to the different GPUs, such that based on the value of a pointer, a load or a store can read to either this GPU, that GPU, or CPU's memory. This is only the beginning. We have a lot of work to do in operating systems, in memory management, and in scheduling. But bringing the programmer view and the operating system view into the heterogeneous space is super critical for us to maintain productivity and ease of use and efficiency in an exaflop scale machine. The third thing that's important is better load balancing and finding more parallelism. Today, Cuda is somewhat fixed in the kinds of parallelism it executes. You program in a grid, you execute a fixed grid over a number of threads, complete, go back to the CPU and execute your next pass. But many problems are more adaptive than just fixed levels of parallelism. So we're looking for and interested in learning more about dynamic parallelism to understand, are there locations where the computation needs to create more parallelism work based on the data set that's being operated on, and spend energy and resources in parallelism, not in the areas of least interest, but where there's lots of activities in a dynamic, particularly in this example, adaptive mesh refinement, where the simulation actually creates new mesh points dynamically as the simulation continues. Today, we're trying to basically build a massively parallel world. And we know the future is heterogeneous, and there's lots of opportunities. As I've talked to you about today, there are many solutions that we need to build to get there. I like to say that there's not just one programmer in the world. There are many different kinds of programmers. And we have to care and feed and help all of our users to bring them onto the GPU. Whether it be with general purpose languages or domain-specific languages like MATLAB, directives, or new languages entirely using our compilers. The new CPUs enable new opportunities for better CPU-GPU interaction and synchronization and communication, and then drive toward building an exascale efficient machine. But another important part of getting there is discovering and sharing. These conferences like GTC Asia are very important to share ideas and learn from each other's ideas so we can accelerate building this massively parallel world. In addition, we have to educate and promote parallel computing as a core part of computer science, and in many cases, other areas of science as well. Parallel programming, even today, is still sometimes considered an advanced topic, a graduate student level topic. Yet, there isn't a processor that is shipped today that doesn't have some form of parallelism in it. We have to make parallel programming part of our core curriculums, because it is the future of where our computers are going. Many people ask me, what kind of research should I be doing? When I go back to my university, how can I take what I've learned here and apply it? Certainly where GPUs are having the most impact in academia is in domain science. People are now learning about what GPUs can do and the performance they can provide, and they're challenging themselves to think outside the constraints that they're used to with traditional CPUs. I encourage you to go back to your university or your institute and talk to your CFD, or mechanical engineer, or biocomputing professor and say, if performance wasn't a problem, if you had infinite number of flops available to you, what kinds of problems would you go solve? Because for many professors, they're making their career out of discovering new problems and doing new simulations they just never thought they could do. Another very interesting area of research is language and compilers. We're not done, and I will admit that CUDA is not the only way to do parallel programming. And there may be many other equally valid or even better ways of doing parallel programming that have yet to be discovered. And I think there's some fascinating research being done in computer languages and compiler technology of how to map and auto-parallelize your code. Directives are getting close to providing a compiler that can auto-parallelize your code. And if we combine that with the right language primitives, we may create some excellent research in productivity programming. The heterogeneous architectures, we feel like the solution is having the most efficient processor for the problem. If you have serial code, you want a very efficient serial processor. If you have parallel code, you want a very efficient, fast throughput processor. And combining those two. Today, the new architectures that are being developed think about different synchronization primitives, atomic primitives, and coherency. How do we do memory coherency and consistency between a very fast serial processor and a very fast throughput processor without hurting performance? It's a very interesting architecture question. And finally, I'll challenge that, and I'll claim that many of the algorithms and data structures that we learned in our first days of learning in computer science as undergraduates, things like linked lists and hash tables and sorting, none of those were parallel. They were just techniques and algorithms that worked for serial processors. But now the world's going parallel. So we have an opportunity as computer scientists to rewrite the book on all of those things. How to do sorting in parallel, how to do data structures in parallel. What are the foundations of computer science are now open to you to define. So I encourage all of you, if you are in computer science, to rethink and publish and invent the new quicksort, linked list, hash table that's optimized and efficient for the new massively parallel world. That was my last slide. I'm happy to answer questions, although I may need help with the translation. Thank you.